This is a joint work with my collaborator in Tsinghua University, Mingyao Qi, and also Ruiwei Jiang from University of Michigan. This is the outline of the talk. I'll get to each part later. So basically, facilitation is a very fundamental problem for a lot of transportation logistic problems. In the standard facilitation that normally we know, we will open facilities. So there are some binary decisions about the opening solution. And then the goal here is trying to satisfy demand and also minimizing the cost. In a competitive facilitation though, you will have two players. I mean, generally you can have multiple players, but here we focus on the leader and follower case. So you can see that basically there are some existing stores in some locations, and then basically you have a leader that selects a set of stores to open, and then the follower will sort of like select their set. They share the market demand, and then the market demand would choose to either go to some of the store owned by the leader or the follower following some utility function. So this is kind of like the problem that we study here. For this type of problem, there are kind of like three classes of literatures. If you think about just the followers problem, given that in the market there's already kind of like some facilities already being opened by someone else, what will be the remaining facilities that they can pick from that will maximize their market share? So these kind of problem has been very well studied, including some of the very recent results by Lubick, Morono, and also Mai and Lodi. And there are some relations of our kind of like work here with them. We focus on this sequential competitive facilitation problem, where we consider both the leader's problem and the follower's problem. So in this case, basically, you can see that the static competitive facilitation becomes the follower's problem in the second stage in this sequential setting. And then you also need to decide the first stage leader's decision in this case. And then there are also some other type of game setting that you can consider this being played iteratively, dynamically, and then eventually you're trying to use some equilibrium results to establish the optimal solution. So that's a different area that we're not going to talk about in this setting. So in this setting, we're focusing on this bi-level problem. If you talk about like how do you model the demand, like how customer choose facilities to go, you can use certain utility functions. Basically, there are two big type. One is their choice is a deterministic model, or they follow some probabilistic choice. So again, if you use deterministic choice model plus some sequential setting that we're studying here, that will give you MILP result. If you use probabilistic choice model, but then in the static setting, not the sequential setting, just the followers problem, that will give you normally the MINLP, which is quite well studied as I show above. Okay, so in our work today, I'm going to present basically we consider the probabilistic choice model. The demand is going to go to either the leader or the follower probabilistically. With this sequential setting. And then now we will have a bi-level program, and each level is a MILP. So that will become much harder to solve, and that's the focus of this paper. So again, there's a lot of existing literatures with this CFLP problem. Is in particular in the sequential CFLP setting, you can consider deterministic or probabilistic choice model. You'll end up with different types of formulation. Our work is the last one here that basically both levels are MILP, and then instead of some heuristic approaches, we use exact algorithm and use branch and cut. The work that I'm going to present to you today also are quite related to some bi-level programming problems, although we're not using the bi-level way of solving our model. We will show you how to reformulate the bi-level into some single level problem. But these are some recent papers that in bi-level programming, how people handle this, MILP structures. And then, and then some of the cutting plane method I'm showing today also being used in these papers in the static CFLP problem. So as I'm showing you these, existing results, let me show you the notation to establish the model. Basically, you have leader that can choose from existing, they already, without loss of generality, you can also assume that there are some sort of like existing facility already being opened by leader and follower. They just need to open new facilities in addition. So the leader's decision in this talk is all X and the follower is all Y. Okay, and then these are binary decisions, whether or not they open some facilities. You can assume that there are some maximum number of facilities that can be either opened by leader or the follower. So P and R are their respective constraint, like their the budget. And then the demand is demand proportion at each of the location I is given by HI. So they add up equal to 1. That's your total market share. And then with certain probability Pij, these demand are going to, in customer I, so in location I, they will go to facility J. So this Pij, basically you can use some your favorite choice model to model it. In here, I'm showing you this multinomial logic example that you probably already seen today in some previous talk. So this Pij will follow some utility function. The higher utility you have with between I and J, the higher chance that the customer will go to that facility. If you consider real applications, basically these utility can depend on, for example, travel distance, right, between these two locations. The shorter I'm away from you, I have a higher chance to go to you to shop something. So then, this total utility, you can just view this as a whole Wij, although it can be calculated with some different functions here. And then, so all the big U L is the leader's total utility, all the big U F is the follower's utility. So if you're trying to model exactly this problem, how it goes, it's a bilevel program. In this case that the leader will choose the X to maximize its market share, and you can calculate its market share using this sort of like a fractional function, right? So the decision that the leader has is X. It will determine what's the total utility they have in the nominator, and also it also depends on what the follower's facility Y that the follower will pick after they see the X. And then the total utility is in the denominator here. So the leader would choose X such that the sum of the X less than equal to P, that's a budget, such that it's given the follower's Y solution. And then the Y solution in the follower's case, they also trying to maximize their own market share this way. And then they cannot open more than R facilities. And also they cannot open the facility that the leader already opened. So this constraint L1E is linking X and Y. And that's why it makes sort of like the reformulation hard in following, okay? So I will go here, we can work with this bilevel program I was just showing you, but we choose not to, and we think, can we try to get a single level reformulation that is equivalent to the bilevel that I was showing you before. So there's just some sort of like a harness result here that basically says that we can't find a polynomial time constant approximation algorithm for this problem unless P equal to NP. And then by kind of like looking at the follower and the leader's objective function, you notice that because they share the whole market, their objective function sum of equal to 1, which means that you can model the follower's problem as the sort of like the opposite of the leader's problem. The follower is trying to choose maximizing its own market share, but equivalent to minimizing the leader's market share, okay? So in that way, you can reformulate the bilevel I was just showing you to this robust optimization way, which you kind of like choose, leader choose an X such that this X will have the follower minimize the same objective function. And this min-max, max-min model is the one we would like to reformulate. And then to solve this max-min model, the problem here is that we can't really just take the dual of the inner problem because of the binary Y we have here. And also if you try to use this constraint generation, like cutting plan, like separation problem and cutting plan approach, it would not work because the follower's feasible region depending on the X. So for the given X, your cut may not be valid for all the X. So that becomes the issue here. And in order to reformulate it, the idea here is that can we reconstruct the feasible region such that the big Y, the feasible region for the follower, is independent of the X solution. So the way to do it basically is the leader's market share function that you see before. If you do a little bit twist here, by changing the x plus y into this, taking the maximum between x and y, and you examine a different function for the leader instead of the original L plus function, basically you can show that these two are equivalent, okay? So in this way, then we start working with this new function L, and then we can show that you can, the bilevel program now becomes this sort of like cutting plan approach that you can implement here to solve the problem. So every time you choose the x, and then because this x here that you reformulate the objective function, and in this way you can get rid of the 1e constant I showed you before. So the problem that we had before was this was depending on x because your y is less than or equal to 1 minus x. You can get rid of that constraint by changing the objective function from x plus y into this maximum term, so that these two problems become equivalent. And then because of the inner problem now, y doesn't depend on the x anymore, and then you can use this cutting plan approach, okay? But what's, if you just like implement this, you will have a lot of issues here because you can see that the L function here is not linear, right? And then even more, you can show that it's non-concave in x. So the relaxation that still remains a non-concave NLP, even the integer variables are relaxed. So in order to, kind of like derive cuts that are linear cuts rather than these nonlinear cuts that we generate into the master problem, there are several ways of doing that. So you can think about some modular inequalities. And so the way that we will do the submodular inequality is by showing the L function is a submodular function of x. And also, can we sort of like find out some sort of like a concave representation so that we can use some of these relaxation sort of like inequalities. And also, just a side thing that we also do some fast approximation to solve the inner problem, although the details are not given in today's talk. So I'm going to show you these inequalities and then eventually how do you incorporate this inequality into a branch and cut algorithm. So for some modularity, basically, if your function has this diminishing return property, then it's a submodular function. So for the fixed y I have in the followers problem, basically, you can show that this L function that we derive is a submodular function with respect to the x decision for the leader. So then, in this way, we can represent the nonlinear constraint that we had with a set of linear inequalities, right, using very famous existing results. But then the problem with these linear inequalities is that they can be exponential number. So then we also show that you can find the most violated submodular cut in this case very efficiently in polynomial time so that you don't have to generate all of the exponential number of submodular inequalities, but only the most violated ones. So this way you can incorporate some modular inequalities into your branch and cut algorithms if you're trying to solve this problem. The other type of cuts you can think about is this outer approximation for the L function. So the L function I was just showing you, basically here you have the maximum between x and y. You can show that you can replace that by this new function in blue color. And these two functions are the same if you take binary values of x and y. But then, this new function can have is more well-defined over the whole continuous interval. Okay. So then you can replace basically because, so first of all, if this new function we design is concave in x, right, then we can replace the cutting plane with the supporting hyperplane of this on this function, but it's not concave. I'm showing you that in the next slides, the picture, okay? So you need to basically continue work on this L tilde function to make it a concave in x. And to do this, basically you replace the xj with this blue color thing. And again, they are the same if you take binary values, but in that case, you can prove that this whole function in 3 is concave. Okay, so this was the original function that was not concave, but what you are doing actually by replacing this whole thing xj with this blue color is to Bauge it, okay? So then we call it Bauge inequality. And then in that case, because it's concave, you just derive the hyperplane, the supporting hyperplane by taking the derivatives. So all the coefficient here, you can calculate it ahead of time for the given X and Y. So it's pretty efficient for these type of cutting plan. In addition to what I just showed you as the two cutting plans, basically you can also use some approximation algorithm. And to do that, we show that the problem I showed you before, if you consider another problem using some parameters in the original problem and derive this mixed integer conic program, second order programming model, basically you solve this mixed integer second order con program. The objective value of that over the original objective value will be bounded in between a given interval. Okay, so the gamma m, gamma big M, gamma small m are all kind of a constant you can calculate in closed form using the problem parameter. And then in this case, we show that it's a constant approximation algorithm. So then you can. It's not possible to improve this result given the theorem 1 that I showed you at the very beginning. And then basically what you need to do now is you're not using a cutting plan algorithm to solve the original problem, but instead you solve this mixed integer SOCP. Okay. But given the advance that are already in a lot of solvers to handle mixed integer SOCP, you can solve this approximation algorithm actually pretty fast. All right, so I can show you some of the numerical results about how we test the different combinations of the method we developed here. This is a facilitation model with like pretty big size. The existing literature I'm showing you here that all study this sequential competitive facilitation problem, and you can see that the I here is the number of locations. J represents the number of demand or customers, okay? So except the first one, which is pretty small size, 35, and then the other one is larger size, but then they all use heuristics. And then the first one use optimization model, but then they cannot guarantee, at the end, they still don't get the optimal solution for a lot of instances. So what we can do is we actually will show you that we solve pretty large problems to optimality. The overall conclusion of the results, basically, if you think about the inequalities I show you, sum modular and Bauge inequality, if you use them together, that's the best. It will accelerate the branch and cut algorithm. The approximation separation procedure I didn't show you also provides a further speed up. And then the approximation algorithm, by solving this mixed integer conic program, can quickly find a near optimal solution in most of the cases. And then I can also show you some solution patterns. Okay, so this is the results. The bold one is the best in terms of time, and that's SC, sum modular, plus BI, Bauge. Okay, in terms of the benchmark, we didn't test the bilevel program. So what we do is basically just enumerate, the number of facilities that can be opened by the leader and see what the follower's best choice is. And then you can see that if you solve that, it will give you a pretty long time for a lot of the big size instances. So you have 100 locations, 100 customers. These numbers are the P and R, how many facilities you can open, okay? But then the speed up is quite significant if you use both inequalities. And then this one also shows you over the time, like after the first, third, 10th lazy back, callback generations, how much you improve the objective function. And that's also pretty significant if you use both, okay? And then if you compare sort of like the optimal way of solving the problem with the approximation algorithm by solving the SOCP, mixed integer SOCP, anything that here says T gap means how much time saving we have. So anything positive says that the AA is better. And then also you may end up with some objective function gap, right? Objective value gap, optimal objective value gap. So as you can see here for the AA that doesn't do better, those solving time are pretty small anyway. So I think there is some sort of like a small difference between the AA and those. But then if the AA is doing good, better than the original, basically those are the ones that it takes the optimal way, like branch and cut, much longer to solve. So overall speaking, AA can improve the the time, especially for those very hard instances, large scale instances, and also they end up with pretty small optimatic gap. Okay, so you can choose to use the approximation algorithm for larger size instances. And if you see what's the sensitivity study in terms of the results, basically this beta will determine how sensitive your customer choice is depending on the distance. So the smaller the beta is, the customer don't quite care about the distance. They will shop anywhere that they like. But then the bigger the beta is, they are sensitive to the distance. So you can see that if they're not sensitive, basically a leader and a follower will try to cluster together to get them as many customers they want. But then if they are sensitive, meaning that they only shop locally, and then the leader and the follower will try to split up the market. Okay, so eventually, like you may think about, oh, what if I want to handle more customers? The number of facilities stays as 100, and in fact, you can increase the number of customers even to 2,000 as you want. And in that way, you have a more granular presentation of the demand. The solution time doesn't change much if you use our branch and cut algorithm. So with that, I'm finishing my talk today. This basically shows you that integer programming method and also a lot of ways of approximating hard bilevel programming problems in this particular setting, sequential competitive facility location setting, how we do it, using value inequality to speed up the computation. And also for the future research, we can compare the results with solving some existing approach for solving bilevel programming models. So with that, thank you for your attention. And I can try to handle some questions.